Thanks for the kind introduction. So my name is Matthias Boehm. This is all about exploiting sparsity and redundancy, which nicely links to some of the concepts on lossless compression, specifically in data-centric ML pipelines. So what is a data-centric ML pipeline? So probably all familiar with the classical ML pipelines of some iterative procedure to train a model, and then once we have this model, deploy this model into practice. Typically, those procedures, they are wrapped into library functions that you can utilize. However, a practical machine learning pipeline usually has additional pre-processing steps, so feature transformations, feature engineering in front of that, as well as outer loops for model and feature selection, hyperparameter tuning. Now, a data-centric ML pipeline wraps additional outer loops for reasoning about data integration and cleaning pipelines, data programming. So how can you synthetically generate additional labeled examples around those inner loops? And on the other side, we have additional primitives for actually model debugging. Is a model with 85% accuracy actually good or not? How can we find this out? Even before that, there is a feedback loop for model debugging, data validation, back to our procedures for data integration and data cleaning. And even before that, we have additional data engineering. Now, the premise of data-centric ML pipelines is that constructing a high-quality, good coverage data set is often more important than small algorithmic changes of the core model we are trying to train. Now, the key observation is that state-of-the-art data cleaning and integration strategies are themselves based on machine learning. So it makes total sense to build those primitives on top of a machine learning system. So I want to highlight two aspects what we build on top of machine learning systems. One is data cleaning pipelines. Great work by Shafak. She graduated last week and built essentially a system for automatically enumerating pipelines of data cleaning primitives, such as data imputation by robust functional dependencies. There are something like missing value imputation by chained equations, where we repeatedly build for categorical numerical columns, classifiers, and regressors to fill in those different values. So given a target machine learning application and an input data set, we enumerate really data cleaning pipelines and tune the hyperparameters in order to find the top K cleaning pipelines that improve some metric on your user-provided target application. And all those different data cleaning primitives are expressed in linear algebra. Many of them are actually sparse. Another example is slice line for model debugging. So what we are given a trained model, we want to find the top K-verse slices, where a slice is defined as a conjunction of attributes such as degree, PhD, gender, female, where the model, instead of 85% on average, gives you only 55% because this slice, this conjunction of attributes, was underrepresented, and you should go ahead and find additional data points. So we introduced an intuitive scoring function that balances slice errors with slice sizes under alpha equals 0.5. It's actually perfectly balanced, so a slice with half the size of the original data set, twice the error, has exactly the same score. Now, we formulated this actually as an enumeration problem, where we look at the entire lattice of all conjunctions of attributes, but we exploit monotonicity. So for degree PhD, gender, female, this slice can only be frequent if both their subsets are also frequent. And if that is not the case, we can prune any reachable nodes in this lattice. So we formulate all this as a fast linear algebra kind of program where, given the input data set, in this case 2 features, red and black, that are one hot encoded, an entire level in this lattice can be evaluated with a single ultra-sparse matrix multiply, and essentially while also applying pruning. Now, those are 2 examples of things we built on top of Apache System DS, which is the machine learning system we are working on for more than a decade now. Our system provides a DSL with R-like syntax, and then provides an optimizing compiler that compiles hybrid runtime plans of local in-memory operations and distributed operations on Apache Spark. Initially, this was an proprietary product at IBM Research Almaden, where I spent first a postdoc and then research staff member time, 7 years in the US. We made it into the Apache Incubator project in 2015, became a top-level project 2017. And the beauty of open source, when I returned back to academia, is I could just fork that system and continue with our entire research group working toward building better and better infrastructure. So over the last couple of years, we even added additional backends, for example, for federated learning, where we can compile those linear algebra programs into federated execution plans. Now, what we learned over the last decade is the separation of concerns of working with abstract data types, matrices, and frames, and implementation agnostic operations allows us to really add additional backends without changing any of the machine learning algorithms and primitives on top of that, which is a huge investment people made in actually implementing those things. Now, in the remaining 10 minutes, I want to talk about two things: exploiting sparsity in this context and exploiting redundancy in terms of lossless compression. So you're all familiar that there's a variety of different sparse matrix formats. So in systemds, we are supporting, of course, dense row major linearized arrays. We support a modified CSR, which is more update friendly, that you can reallocate individual rows separately. We support CSR and double compressed CSR, as well as coordinate format. And systemds actually automatically, during runtime, measures the number of non-zeros and automatically switches between those representations. Now, in terms of sparsity exploitation, of course, we have all combinations for all hundreds of operators, essentially to do all combinations of sparse and dense inputs. In the literature, there has been then additional work on how we can exploit sparsity across entire chains of operators. So this is not from our group, this is from Duke University, but the first author was an intern at IBM in our group as well. So what they are doing, they essentially, from a sparse matrix, a sparse driver O here, compute a mask and feed this mask into an entire subtree of operators to only compute the cells that are actually relevant. What we are doing instead is we similarly rely on a sparse driver. So this example comes from matrix factorization. So you have an ultra sparse ratings matrix, often 10 to the minus 8, 10 to the minus 7, X. And in this case, we're computing the squared loss. So in matrix factorization, we want to compute a low rank approximation, U matrix multiply V, that roughly approximates X. Now for the squared loss, you see that we compute this outer product, which creates a dense intermediate, minus X, another dense intermediate, squared, another dense intermediate, and then this element-wise multiplication with W, which prunes away most of the computation. So what we do instead is actually we compile a source code for the entire chains of operators in order to exploit sparsity, iterate over the non-zeros in X or W, and only compute dot products when needed. So this comes to our spoof code generation framework. So here we see our basic compilation chain, and as part of this compilation chain, we invoke our CodeGen compiler, who identifies subtags of operators to fuse, then generate code, load this generated code as an operator back in, and treat them as a normal operator in the remaining compilation chain. Now later we added an actual cost-based optimizer that finds the exact cost optimal plan for those fusion plans. There are different templates we are supporting. So here's an example of a basic L2 regularized support vector machines, kind of two loops. The outer is for a conjugate gradient method. The inner is for a line search, how far in the direction of this gradient we are getting. By default, we compute plans like this. So it starts at the bottom and computes the results on top. Our normal fused operators that we hand-coded often only cover 2 or 3 inputs. This is good. This already reduces the number of vector intermediates from 10 to 4. But what our code generation framework does, it takes the entire inner loop and compiles a single fused operator for it. And what you see here is we actually just compute for a single cell that we pipe through all those operators, all the different computations we do, and compute ultimately 2 aggregates that are used for the convergence check in the surrounding loop. So what worked extremely well for us is to have hand-coded skeletons that handle actually cache blocking, multi-threading, the entire access to different sparse representations, to compressed representations, and only generate really the custom code what happened per value or per data item. Similarly, we supported for row, piping entire rows through those fuse operators, which is important if you have in a DAG those row aggregations, for example. Again, it gives us a DAG. Ultimately, we compute little intermediate representations, and generate Java source code that pipes individual vectors, dense or sparse vectors, through those computation graphs. In the last couple of years, we did a similar backend for GPUs as well, where you have additional steps of reordering rows in order to create more regular structures. Now, in terms of performance, we compare against TensorFlow, XLA, and Julia. So for this first example, the sum of 3 matrices element-wise multiplied together, you essentially see that our base is kind of the, without any fusion, generated is our generated operator, and fused is the handwritten fused operator. So you see that there's an order of magnitude actually benefit of doing this kind of fusion. Interestingly, for the sparse case, where you have 3 matrices and you want to exploit the sparsity of all 3 simultaneously, in this case, we get even better performance than fused operators, whereas Julia, even the fusion reduced performance, so made it slower, because if you're not careful about sparse access, every access in the CSR will create a binary search, right? So you need to keep stateful iterators and actually linearly scan those representations. For more complex matrix vector multiplies, where you can actually transform 2 scans of X into a single one, observing that an computed intermediate is joined against the exact same row where it was computed from, you get similar performance. And in this case, it might be partially unfair to TensorFlow because they focus primarily on hardware accelerators, and this is a CPU computation. But back to sparsity exploitation. So here we have another kind of cross-entropy loss in matrix factorization scenarios, and you see on the x-axis how we vary the sparsity. So sparsity of 1 means completely dense, and as we go by orders of magnitude, you see you get orders of magnitude better performance. Now, this is basic sparsity exploitation, but I want to make a case that redundancy exploitation, so lossy compression, is actually a generalization of sparsity exploitation. So let's look at a couple of data characteristics. So classical data sets like COF type, so forest cover, that you see you have often way more rows than columns. In those tabular data sets, you have varying sparsity per column, per feature that you have. Furthermore, you have often very small column cardinalities, so a number of distinct items compared to the overall number of rows that you have. And furthermore, you have a lot of column correlations. So on the right, you see, for example, a census data set where almost every column is correlated with every other column, which makes a case for co-coding columns. And you see actually that the compression ratio that we got increased by almost 3x by exploiting those column correlations. So our prior work on compressed linear algebra applied lightweight database compression techniques to individual columns of a matrix. We did co-coding, and we selected heterogeneous encoding for schemes for the different columns. Then we encode an uncompressed matrix into those different things. So one scheme, for example, is DDC, which stands for dense dictionary coding. We encode the distinct items in the dictionary. Every value becomes the position in the dictionary, which then also identifies how many bits we actually need to represent it, which reduces memory bandwidth requirements and allows us to make things much faster because some of the operations can be directly computed on the dictionary instead of all the different rows. Because it's heavily data dependent, we actually do sample from the matrix and then make all those decisions what to co-code. To show you that we can perform linear algebra directly on this compressed representation, here's a simple matrix vector multiplication. So we have 5 columns, a vector of 5 elements. We essentially scan through the distinct items. So in this case, it's run length encoded. We pre-compute the multiplication with whatever value in the vector is, and then go over the compressed index structures and add this to the output. Now for co-coded columns, like in this case column 1 and 3, we actually have a pre-aggregation on the dictionary. So you have multiple columns, you do multiple multiplications and additions, you pre-aggregate this and only add this pre-aggregate to the output, which reduces the number of floating point operations. Coming back to those lower bounds, even for dense and sparse, it's heavily data dependent. You can get arbitrarily fast with a constant matrix, for example. And you do that, and you scan through them, and ultimately you compute the same result. Now, because this scatter into the output can be really slow, we then did cache-conscious kind of segment-aligned scans where we can bound the working set on the output vector, and similarly it works for vector matrix multiplication. Just a quick set of experiments. So in terms of compression ratios, we are outperforming lightweight schemes like Snappy and LC4. We sometimes even outperform heavyweight schemes like GZIP. But notably, so here we use the InfiniMNIS data generator, generated all the way up to a terabyte. What you see, if our matrices fit in memory, we are very close to uncompressed operations. However, if the data is larger than memory, so in every iteration we have to read partitions in, there by the compression ratio, we actually outperform uncompressed representations. And recent work of one of my PhD students actually now does this in a workload-aware manner. So we are actually, while compiling the plan, we see what kind of operations we perform. And instead of optimizing for compression ratios, we're optimizing for execution time. So if your data fits comfortably in memory, you should optimize to have faster operations. If your data does not fit in memory, you should optimize for compression ratios. Recent work, so that was the aware work. Our next is the beware work, where we push compression all the way into feature transformations like one-hot encoding, recoding, feature hashing, where there's a lot of potential. So instead of applying those structural transformations and then rediscovering redundancy, we go all the way to the sources and exploit this redundancy. We see a lot of redundancy in data-centric ML pipelines. I want to make a case for sparsity and redundancy exploitation. Both are super critical, but redundancy exploitation is even a generalization of sparsity exploitation, and both need optimizing compiler and runtime infrastructure. We are really doing system-oriented research in my group. It's all about finding the appropriate abstractions and the right collaboration. So I hope to talk to many of you during this conference. Thank you very much.
Sparsity and compression stuff. Some of this stuff is new, so I'm really glad to find that. So questions? So if you are looking at compression, so have you looked at more structured data type compression, like a block structure and stuff like that?
So right now we're doing lossless compression. The mainstream, however, is lossy compression. And what we are currently doing is we separate things. So we actually, at the algorithm level, at DSL level, we are trying to learn both sampling, data augmentation, quantization schemes, but we include essentially those decisions into the loss function. One aspect of it is I want only kind of 3x3 blocks of cells to preserve this regularity for GPUs and other representations. But we strongly believe that what we should do inside our system should focus on lossless strategies, because that is really trustworthy. You can guarantee the exact same results. And the other things, however, can be pushed at algorithm level, and you get the benefit
because
of both worlds.
A lot of machine learning, you can actually play with the algorithm level too, and get more compression in there.
Excellent question. Yeah.
Any other questions?
So on the data-dependent optimization aspect, you mentioned that you have basically a cost-based optimizer. And actually, one of the interesting problems in cost-based optimizers is basically to propagate the sparsity information.
So excellent question. So it's about sparsity estimation. So we had a Sigma 2019 paper where we introduced the MNC sketch. And what we did there is compare. So there are a couple of really good estimators, like the layered graph, super high accuracy by Edith Cohen. A super underappreciated paper from the end of 90s, has only 50 citations or so, is super accurate, but relatively expensive to construct. It's a graph that has an edge for every non-zero and a node for every row and column in a long chain of matrix multiplies. So we added a more cost-effective sketch, and we integrated it into a dynamic programming optimizer for finding the optimal parameterization for matrix multiplication chains. This was experimental work. It worked quite well, but we did not fully integrate it by default in our system, because sometimes the overhead of creating those sketches, you don't know if it will be amortized or not, if you ultimately end up with completely dense representations, for example. At SIGMOD 2 weeks ago at Santiago, there was actually a follow-up work by another group that followed up on our MNC estimator and got even better results. Casting this entire, you have a chain of matrix multiplies. We should not just think about compilation and subsequently executing this plan. It's just a joint thing. And ultimately, we should measure the execution time of both optimizing and executing the sparse chain of matrix multiplies, and there's a lot of potential in that. Excellent.
Okay.
Thank you very much.
Thank you.